Ethanal reacts with potassium cyanide followed by dilute acid to form 2-hydroxypropane nitrile. Name the mechanism for the reaction between potassium cyanide and ethanal. Ethanal is an aldehyde, and so the cyanide ion has a lone pair, it's a nucleophile, it's going to come in, it's going to add, and then the acid is going to add on in the next step. So we've got a lone pair on there, a H, we've added the cyanide, and we're now going to go and get an acid. So we used a nucleophile, a lone pair donor, and we added it. We didn't knock anything off, so it's nucleophilic addition. The 2-hydroxypropane nitrile formed in this reaction is a mixture in equal amounts of two isomers. It's a mixture of the optical isomers. Name this type of mixture. An equal amount is called a racemic mixture. And say why the structure of ethanal leads to the formation of two isomers. Well, the C double bond O part of ethanal is planar, and the CN minus nucleophile can attack from either side, above or below, of the plane with equal probability. So we're equally likely to get it attacking from above and sort of folding the plane, the three bonds down, or attacking from underneath and folding the three bonds up. Then it wants us to show 3D representations and show the relationship, non-superimposable mirror image isomers. So we're looking at our hydroxynitrile and we've got the C in the middle here. We want to be drawing a tetrahedral arrangement around it. And then we want to draw the mirror image of that. So the wedge and the dash to the left instead of the right. We want to think about the four groups in our 2-hydroxypropane nitrile. So propane nitrile with a hydroxy on number 2, a H, and then this group would be a CH3. So our four groups that we need to arrange. Now it doesn't matter where you put them on the first structure, those four things, as long as on the second structure you reflect their positions. So because I put the H on the dash line, it goes on the dash line, the OH on the wedge goes on the wedge, the cyanide at the top, and the methyl on the outer one. 2-hydroxypropane nitrile can be used in the synthesis of the monomer acrylonitrile. So we can see here, if we go back to our 2-hydroxypropane nitrile, had an OH and then a CN. We've lost the OH and then one of these H's from the CH3. So we're eliminating from an alcohol, and so the elimination from an alcohol needs a concentrated catalyst. So concentrated sulfuric or concentrated phosphoric are often used, and it needs to be hot. It needs to be very hot, high temperature, so you may say reflux or heat or high temperature or hot. I'm going to write reflux, but you might have written high temperature. And then we need to draw a section of the polymer showing 3 repeat units. So if you can just like sketch out the acrylonitrile in what looks kind of like starfished shape, where its arms and legs are sticking out, you can think about how when that goes up and down, how those stretches itself out, how those groups will align. So 2 H's and a H and a nitrile. Make sure that your C is bonded to your C, and then we've got to repeat it 3 times. So the left hand one has HH and the right hand one has HCN, making sure your connectivity is to the C of the CN and not to the N. And then finish off with trailing bonds.